All right, so this question is a little bit tricky because I've chosen some quite yucky numbers to graph. So I feel like explaining it in a video is a little bit better than just on writing because you're going to be like, what the hell? So I want to explain the thought process behind this question. So first, let's rewrite the equation. It's going to be y equals 5 onto 10 of 3x minus pi, and then all of that minus 1. And the domain, put the domain down here, is going to be this. So a little bit of a sort of irregular question. It's one of the harder equations, I would say, to graph because of the way that I've constructed it. But if you know how to do the hard one, then the simple one should be easier. Okay, so first thing we should do when we're considering what to graph is, well, let's look at the horizontal bit. You see how the 3x and the minus pi, it's not factorized yet. Okay, so I haven't factorized it. The 3 is still on the x, and then the minus pi is on the outside. So we need to make sure that we account for that. So I'm going to change that straight away to be 3, and then in brackets x minus, and we have to factorize the 3 out, so we're going to go pi on 3, right? So we put it over 3, then the 3 cancels to make just the pi. Okay, so we've adjusted for it. Okay, so now that we have this, we can interpret it. The first thing we do, and I've already drawn the graph out here for you, but there's also some thought that goes into how I should graph this. Firstly, I want the graph to, I've used a grid paper here, but if you're in an exam, you might need to just use your ruler. I've made the graph 6 by 6, okay, or 12 by 12, I should say. And so the reason why I've done that is because if you pick 12, so from here to here, it's about 12 squares, same from here to here. If you pick 12, it's a nice number because you can divide it by 2, 3, 4, so it allows you to account for a lot of different graphs, including the the trig ones, where you'll often get like pi's on 4s, on 2s, on 3s. So 12 is a nice number because it's very versatile. You can always just put 12 in and then you'll be able to account for all kinds of graphs with those factors. So I do 12 and a bit, so I leave like half a centimeter at the top and the bottom, so it's a total of like 13 centimeters for each side, so that I can write that arrow bit without it, interfering with the top part. And so yeah, that's what I do. Then you also want to consider, with just a general sort of look at the question, what does it generally look like? Whereabouts will it be? So yeah, we want to sort of generally look at what this graph is doing. Okay, if this was, in this case it's a tan, but if it was like a sine or a cos, right, you know how it sort of circulates like that. For example, we wouldn't want to do something like this because we're just sort of wasting this top bit if the graph was like all the way down here, for example, but it's a -1 and then it's like, this is 5 on 2, so it's about 2.5. So it'll be like around -1, not too far from the center, and then 2.5. So we sort of we need both ends of this in order to take the full graph. So this drawing it out evenly is fine. Okay, we don't need to like shift this up or down to accommodate. All right, but in this case it's a tan as well. So this center graph would actually be good, right? Because the way that the tan function looks is it goes all the way up and down, right? So we need sort of the full thing, I guess. But also, I guess it's because the center is at -1, so it's still close to this thing, so it's going to be evenly spread on both sides, I guess. So you don't need to adjust the graph for that. Okay, now what should we start with? Well, the 5 on 2 in this case doesn't really affect the tan function. Okay, it's a vertical dilation in this case. In a sine or a cos function, it would, right, because it affects the top and the bottom lip. But for the tan, it's sort of like, it just sort of stretches it like to be a bit steeper or a bit flatter, depending if it's a bit smaller. So it doesn't really affect it. So you don't really need to consider it that much for the tan function. However, we do need to consider the horizontal dilation, and also the horizontal translation, and then of course the center. So we need to think about what a normal tan function looks like without all these transformations, and it looks something like this, right? And also the normal bit that the asymptote is only at pi on 2 and then minus pi on 2 for the other side. Okay, that's what it generally looks like. Okay, and it just keeps repeating like that in that manner. But in this case, we have some transformations. The 5 on 2 doesn't really matter, but the center is going to be minus 1. So instead of it being like there, it's going to need to go, oh sorry, it's a minus 1. So it's going to go down like that. Okay, it's just going to shift down. So that the point at which it's sort of this, you could sort of call it the point of inflection, is going to, that point of inflection is going to be at the minus 1 bit. Okay. Now, as for the period, it's a little bit different to the sine and the cos one. If you have like here the period is it's going to be 2 pi over whatever this number is on 2, so the period is that. But in this case, for tan, it's a little bit different. It's not 2 pi on whatever it is, it's just pi on whatever it is. Okay, not 2 pi. And the reason for that is because a period normally for a tan is actually just pi, the distance. But for sine, it goes like from 0 to 2 pi, it's this whole cycle. Okay, but for tan, it's just half of that. So it's a different starting period that we're with. Okay, so the period is going to be pi on 3. So it's not going to be pi. And so when we're doing this, this is pi across. So we're going to need to sort of split this bit in two now, right? So for when it was normally pi, it was just pi on 2 on here and pi on 2 on here. Now we need to split pi on 3. And one way we could do that is, well, pi on 3 is the same as 2 pi on 6. So now I have 2 of the pi's here. And now I can split it up into pi on 6 and pi on 6. So it's going to look like this. Oopsies, I should leave that there. It's going to look like that. But now these bits are going to turn to 6 and 6. Okay. And then the last bit that we need to consider also as well is that it's a plus by pi on 3 to the right. So because it's a minus, so you go to the right pi on 3. And so this whole thing shifts to the right by pi on 3. So instead of being at 0, it's going to be at pi on 3. So it's going to be like somewhere here. Okay, because that's pi on 6. So 2 pi on 6 is here. That's pi on 3. So it'll look like that. Okay. Now, I know you might be wondering, well, it's easy to do the transformations if you draw it first and then, you know, annotate it with the normal parameters, and then just sort of shift it and change the drawing on top of each other. But in an exam, right, you can't just like draw a bunch of different graphs and then it overlaps with each other and then like draw the actual proper final one on top of it. Like that's just not really going to work. And so that I say, yeah, you're sort of correct. Like you can't just draw graphs on top of each other or messy like. You have to do the final graph, unless you, generally speaking, you have to just do the full final graph on its own. However, you can still visualize it without having to draw it. But if you also really just want to draw it on paper, what you can do is instead of drawing it on the graph that you will use for your final transformed graph, then you can just maybe have like a little mini one off to the side or below, which you can maybe like just cross out later on, and you could just use it as a rough sort of sketch to sort of be like, okay, that's, you know, where my parameters are, and then you sort of do the transformations here on your own. So it goes down by 1. It needs to be, you know, a period of pi on 3. So, you know, this is going to be pi on 6 and pi on 6. And you shift it across pi on 3. Like you can do that all in like a mini scale, in your own messy whatever way, and then transfer that, maybe cross it out, and then do the final proper one on the graph here. You can do that if you like, or you could just visualize it without having to draw it. It's up to you. So first of all, it's going to be the normal. You just have to have it in your mind, I guess, what the normal trig tan graph looks like. So let's first deal with like the period, let's say. Well, okay, -1 is pretty easy, like to think about. It's just going to be the whole thing down by 1. So actually, well, actually, no, you don't need an asymptote for that. The next thing we can deal with is the period. So normal period is pi. You need to remember that for a tan graph, and so it's going to be over 3 for the period because this is a 3 in here. And so instead of going from pi on 2 to minus pi on 2, it's going to go from, and you need to, it's going to go half of this, which is going to be, you know, pi on 6, right? If you divide this by, dividing it by 2 is sort of like timesing the 3 by 2, because, you know, pi on 3 divided by 2 is just times by 1 on 2, right? You do the reciprocal of it and you multiply. And so that should give you pi on 6. And so it'll be pi on 6 and minus pi on 6, right? For a full period of 2 pi on 6. Okay, so it's going to be down 1 and have pi on 6 and minus pi on 6 for one period. And we want to do this for pi on 2 to pi on 2, so I should write that straight away. Zoom in here. Okay. And then the last thing we need to do is that's shifted pi on 3. So actually we're doing it in terms of pi on 6s. So let's just write, well, 2 pi on 3 is already in terms of 2 pi on 6. So 2 pi on 6 it's going to be shifted to the right. Okay. So since it's shifted to the right by 2 pi on 6, this is also how I like to think about the horizontal shifts. Always think about where the center is, and it's normally just going to be at 0, right? So you consider one point of this graph, and then you shift that along to where it would be. So it'd be like 2 pi on 6, and then you draw it there. Okay, and so you always just remember everything moves just like that point, okay, across. But you sort of use one point as a reference. So I'm going to use my center point because it's a nice little distinct reference point. Okay, so pi on 6. Well, let's put everything in terms of pi on 6s, so that's easy to understand. Pi on 2 is 3 pi on 6, right? Okay, so from 0 to 3 pi on 6, we're going to shift it 2 pi on 6. So, and this is why it's handy to have a 12 by 12. So there's 6 in here. So a pi on 6 is going to be a third of that, right? Because this is 3 pi on 6. And so if we want 2 pi on 6, we go to this 2/3 point, right? There's 6 here, so you go 4 across. And so that's going to be where the center of the graph is, okay? And so it's going to be, that's going to be where it is, sort of. But then we got to remember, okay, it's down by 1, so it's going to be down here. And then the period is going to be, finally, the period is going to be minus pi on 6 and pi on 6. So pi on 6 on either side, right, for a total of pi on 3. And so, well, that's pi on 6 to the left, that's pi on 6 to the right. And so you can just draw this graph here, and then it's going to go to the center here. So the asymptote is going to be here. Okay. And it's going to go something like this. Okay. And the intercept probably doesn't really matter too much. Unless they probably specify that you want to find what that is. Okay. And this is, it looks the same as this one, but that's only because I drew this one with no regards to scale. But that was supposed to be a little bit wider if I was considering it as the normal one without any transformations. Okay. So that's what it looked like. And then, well, you got to do it for the rest, right? So it's going to just continue that pattern. So that's going to be the next one. So the asymptote is going to be here too. And then that's it. So the next asymptote is going to be here as well. And so you have 3 of them. Go here, just like that. And another one at the 1 point. And we should specify that this is -1. Okay, so that's generally what your graph will look like.